In this study, we will focus to solve the second order linear homogeneous PDE. This is the general equation for the second order linear homogeneous PDE, where you can see there are 3 second derivatives and 2 first derivatives here. You have 7 constants in the equation, where A, B, C are the constant to the second derivative, D and E are the constant for the first derivative. From this PDE, what we want is we want to solve the U with respect to X and Y. U is the dependent variable here, X and Y are the independent variable. In engineering application, we are more interested to find the particular PDE solution instead of the general PDE solution. This can be done by applying the boundary condition or the initial condition. Before we proceed to solve the PDE, you must know how to classify the category of the PDE. This can be done by evaluate the constant A, B, C for the second derivative here. So you need to compute this formula, which is the b squared minus 4ac, and from the value you can classify the category for the PDE. When you obtain the b squared minus 4ac less than 0, this is known as elliptic PDE. If b squared minus 4ac is equal to 0, this is parabolic PDE. If the b squared minus 4ac is greater than 0, then it is called the hyperbolic PDE. For example, let's try to classify this PDE. So you need to arrange it according to the general formula here. So we need to move this term to the left hand side, then you obtain negative du over dt, which is equal to 0. By comparing the coefficient for the second derivative here, you see a is equal to 3 here, b and c are equal to 0 because you don't have this component here. Therefore, from here you substitute inside this formula, you have 0 minus 4 multiplied with 3 and then multiply with 0. So you should obtain 0. So if b squared minus 4ac is equal to 0, then this is known as parabolic PDE. Let's try with the second example here. We shift the term here to the left hand side so that you obtain the general equation. Let's compare the general equation with this equation. Then you see the a is equal to 1 here, b is 0 because you don't have this component, c is equal to negative 1 here. Therefore, these are the results for ABC. You substitute inside the b squared minus 4ac and you should obtain it to be 4. 4 is greater than 0, therefore we can say that this is hyperbolic PDE. Let's classify the category for this PDE. Let's compare it with the general formula here, where a is equal to 1 here. So you don't have this component, therefore your b is equal to 0. Then you compare this component with this, you obtain the c equal to 1. Substitute this information inside the formula b squared minus 4ac, you should obtain the value equal to negative 4. And this is less than 0, therefore we know that it's an elliptic PDE. So why we classify it into these 3 categories? In general, elliptic PDE is to model some engineering application with steady state behavior. It means the physical quantity that you are interested is remain constant or doesn't change with respect to time. Laplace equation here is one of the examples for the elliptic PDE. In this problem, you want to find the temperature change with respect to x and y location. The temperature change with respect to time is equal to 0 in this case. Therefore, the temperature that you found from here is called the steady state temperature. On the other hand, the characteristic for the parabolic PDE is the time variable for the physical quantity. Heat conduction equation here is one of the examples for the parabolic PDE. In this case, you want to find the temperature change with respect to x location. Not only that, you want to find the temperature change with respect to time as well. Since the temperature will change with respect to time, therefore in this case, we call it as the time variant case. The temperature that you found from this PDE problem is transient and it will change over the time. Hyperbolic PDE is also similar to the parabolic PDE here, where the physical quantity is time variant. Wave equation here is one of the examples for the hyperbolic PDE. In this case, you want to find the variation y in the x location with respect to the time. This means that the variation at various points will be different and the variation will change with respect to time. The main difference between the parabolic and hyperbolic PDE here is that the physical quantity, the temperature, changes with respect to time in the first derivative. For the hyperbolic PDE case, the physical quantity, which is the variation in this case, is changed with time with the rate of second derivative. This will cause the vibration here oscillate over the time. For example, the temperature change here will be reduced over the time and there is no oscillation. But for the wave equation here, after you solve the vibration y, then you obtain the vibration change over the time in the oscillation manner. So this is the main difference between the parabolic and hyperbolic PDE. Both cases has the transient result, which is changed over the time. In addition, parabolic PDE has the result with no oscillation and hyperbolic PDE has the result with oscillation. You obtain the steady state result for the elliptic PDE, where the result is just constant and remain the same all the time. Previously, you have learned that the heat equation here is one of the examples for the parabolic PDE. Let's have a root which has the initial temperature equal to 25 degrees Celsius. At T greater than 0, you put some heat source on both ends of the root. For example, the temperature for the heat source here is 80 degrees, therefore the end here will have the same temperature. On the other end, we put some heat source with 40 degrees Celsius. Let's assume this direction to be x direction. So the length is from 0 here to L. Therefore, you can see at x equal to 0 here, the temperature will be equal to 80 degrees Celsius. At x equal to L here, the temperature is equal to 40 degrees Celsius here. At t equal to 0, then your temperature is 25 before you apply the boundary condition where you put the temperature 80 degrees Celsius and 40 degrees Celsius and both ends. So immediately after you apply this boundary condition at t greater than 0, then you have the temperature curve like this initially. Since you apply the heat source at both ends here, therefore the temperature here is remain the same 80 degrees Celsius and 40 degrees Celsius over the time. So it doesn't change with respect to time. It just remains at 80 and 40. So what we are interested here is we want to know, for example, at x equal to L over 2 here, at the middle of the root, what is the temperature change over the time? So you want to know the temperature at a particular x location and the temperature change with respect to time. So how can we calculate this? Engineers and scientists has modeled this PDE in order to solve the temperature change with respect to x and time. If we know the material property for this root, then we can solve the PDE. For example, the K prime here means the thermal diffusivity, which can be found from the thermal conductivity divided by the density and the specific heat here. For example, if this root is made of aluminium, then the thermal conductivity will be around 0.49. The density for the aluminium is around 2.7 and the specific heat is around 0.217. So by calculating this, you should be able to obtain the thermal diffusivity, which is equal to 0.835. Bear in your mind that the coefficient in PDE is meaningful, is obtained from the material property or the system characteristic. In this study, we will mainly focus on how to solve this PDE problem and obtain the corresponding result. For the parabolic PDE case, you should obtain the result in transient, which is changed over the time, and non-oscillating. The previous heat equation has only one dependent variable u and two independent variables x and t. So this is known as one-dimension heat equation, where you have only one dimension in x location. You can also have the two-dimension and three-dimension heat equation by include additional term here in the y dimension. In this case, you solve the u in two dimensions, which is x and y dimension, with respect to time. If you have additional two components here in the y and z dimension, then you can solve the u in terms of 3D, which is x, y, and z dimension, with respect to time. In this study, you should focus to learn the separation of variables method in order to obtain the solution from the parabolic PDE here. This method can be applied to solve the 1D until 3D case. However, in this study, we will focus to solve the one-dimension heat equation, and these two cases are out of the scope. In this study, you will learn how to solve the wave equation here, which is a hyperbolic PDE. For example, you have a guitar string here, which is fixed at both ends. Let's plug the guitar string. So you pull the guitar string, and then at t equal to 0, this is the shape of the guitar string. When t is greater than 0, you release the guitar string and the string will vibrate. Let's say this is the vibration pattern for the guitar string at t equal to 5 seconds. So over the time, let's say t equal to 10 seconds, you see the vibration reduce. As time goes, the vibration of the string will be reduced further and it will become 0. We can model this problem by using the hyperbolic PDE here, where after you solve this PDE, you can obtain the vibration at y, which is in this direction, with respect to the x location here, and it will change with respect to time as well. So we can say that the solution for the hyperbolic PDE is transient, which can change over the time, as well as oscillating. So in this study, we only focus to solve the one-dimension wave equation here by using the separation of variable method. So you want to find the u with respect to x and t in this case. So for the 2D and 3D wave equation like this case, where you want to find the u in terms of x, y, t, or you want to find the u with respect to the x, y, z, and the t. So this is out of the scope and we don't cover this. In the last case, we will learn how to solve the Laplace equation, which is an elliptic PDE. The physical quantity that we are interested here is t, which is changed with respect to x and y location. This physical quantity is steady state and remain constant with respect to time. We can use this PDE to model several engineering applications here, where you can see the temperature distribution on this plate due to the boundary condition here will be steady state. So you want to find the temperature change with respect to x and y location. For example, if the boundary condition here is given, let's say you want to find the temperature at this point, which is at x equal to 2 here and y equal to 4 here. So you want to find the temperature at x equal to 2 and y equal to 4. So by solving this PDE, you can find this answer. Not only the temperature at this point only, in fact, you can find the temperature distribution at the whole plate here. The elliptic PDE can be applied for the second case here, which is used to find the steady state velocity of the water flow under the dam. It can be also solve the steady state electrical field near the conductor. So you have the one-dimensional Laplace equation here, where the u is in the x dimension only. For this type of problem, we can use the basic technique to solve it, such as the integration, solve PDE like ODE technique, or the reduction of order method. Our focus will be the two-dimensional Laplace equation here. So after you solve this, you should obtain the u in the x and y dimension. We can solve this by using the separation of variable method. This method can be applied to the three-dimension case as well to obtain the u in the x, y, z dimension. However, this is out of scope in this study. In this case, you have one-dimension heat equation with the heating element, one-dimension wave equation with the forcing function, and one-dimension Poisson equation with the heat element. If the right-hand side here is non-zero, then you will have non-homogeneous problem. Solving non-homogeneous problem will be out of scope in this study. So we don't cover this in this study. We only cover the homogeneous problem where you have the right-hand side equal to 0.